Hey everybody, welcome back to Young Engineers of Today. I hope you had a good couple of days. And I hope you're ready to continue with Bridge Designer because that's what we're going to do. We're going to do that, continue with that, do that thing, build bridges and stuff. And, you know, uh, potentially that could be a really interesting thing. You could find your calling here, who knows? I don't know. Anyway, that's what we're going to be spending today doing, and potentially Monday as well. What's the website called again? Well, here you are. There you go. That's the download link for everybody. Just in case you need it again. But yeah, go ahead and download the 2015 version just so we've got everybody on the same page. And obviously for your operating system. And we can words. I apparently have been very scatterbrained today. All right, so yep, give everybody a minute in order to download that. Spend some time going over what we went over on Monday. We went over a lot of stuff, so really it's understandable if you don't remember everything that we went over. And that's not necessarily my intention right now is to sort of reinforce everything. I'll briefly go through everything that we went over, but you know, we'll be familiarizing ourselves with these forces and everything a little bit more as we work with the Bridge Designer software. What's up, Cohen? What do you mean it isn't valid? What are you running? Yeah, but what are you running? That's weird. That shouldn't be. It's less than a year old. Um, hmm. Oh, geez. Trying to think here. Maybe. What does it say when you try and run it? Anything? The date is before or after the time period for the valid certificate. Okay. Okay, that's something I've never heard before. Is it when you're trying to run the installer, or is it when you're trying to download the software? Oh, okay. That was the thing I was explaining on Monday. Um, that's just because they haven't updated the certificate for the site. But you should, certainly if you're like using Chrome or something like that, you should still be able to navigate to the website. You'll get that notification. It's like, oh, you can't come here. There should be a link labeled advanced at the bottom of that explanation. If you click on that, it will expand advanced options, one of those options being continue to the site anyway. Um, I know I went over it quickly on Monday, but that was what I was trying to, yeah. I was going to say, I was like, that unless you're running like a quantum supercomputer, your computer should not be too new for this. Yeah, no, that's unfortunately the Bridge Designer Contest people went defunct this year. Um, so they keep the website up so that people like us can download um, the Bridge Designer software iterations and stuff like that, but they're, I presume, not going to maintain it anymore, which means that from here on into the future, we'll probably continue to run into that issue, which is unfortunate. It's kind of sad that that happened, but sometimes, sometimes these things happen, present tense. Anyway, yeah. Also, installing the software is pretty straightforward. You just keep clicking the next button and then launch the software when you're done. But yes, in the meantime, forces associated with the bridge, with bridges in general. You've got compression, which is smashing force, and then you've got tension, which is pulling force, and then you've got shear, which is twisting force or bending force, that whole sort of thing. All bridges experience these. They also experience different ones in different parts of the bridge, and you'll certainly see this illustrated in sharp detail when you're simulating your bridge. You've got loads which generate those forces, like dead loads. Um, you, you just click the link for download. So like if I want the one for Windows, I just click the download link. Um, and that should be it. It should take you to a SourceForge page, and then it will automatically download it after a certain period of time. But that should be all you have to do. But yeah, so dead load is the weight of the bridge itself. Live load is the weight of the bridge is carrying, and that could be either still loads, static loads, or moving loads, dynamic loads. There are thermal loads, which are just, weather causing things to contract and expand by heating them or cooling them or whatever, and not necessarily, related in order. Earthquake, pretty straightforward. The earth shakes, bridge hurts. Wind, also pretty straightforward. Wind blows, bridge hurts. Yes, it does take you to SourceForge, at least for the 2015 version. Um, but yeah, it does take you to SourceForge. Oh, you're fine. I just want to, yeah, it's good to make sure that we're all on the same page. All good though. I apologize too. I'm fairly scatterbrained right now. Yeah, anyway, these loads can generate those forces on a bridge. All pretty self-explanatory stuff. The weight of the bridge, the weight of the stuff on the bridge, um, as subcategories, stuff on the bridge that's moving or stuff on the bridge that's not moving, how the stress is caused by temperature changes, the stress is caused by the earth shaking, and the stress is caused by the wind blowing. To that end, there are different materials you can build a bridge out of in order to combat these things. So you've got wood, which is good and cheap, but you have to replace it. It can also catch fire. Concrete, which is good and cheap, handles compression pretty well. It's fireproof. However, it doesn't really handle tension well and is affected by temperature changes. Not specifically fire, but just, temperature changes. Reinforced concrete, which is good, and it solves the tension issue of regular concrete. It's low cost, and it's, additionally fireproof and weatherproof. However, it still has issues with temperature changes. And then cast iron, which is strong. You can form it in any shape. It's fireproof, but it is expensive and it doesn't really handle tension well, and there's no real warning before it breaks. And then steel, which does a fantastic job of holding up. It's very resilient, very strong, but it's expensive. The shape of the bridge also affects how well it holds loads. Rectangular bridges being not that great, but arch bridges being stone, like a brick and mortar or a stone and mortar sort of thing. Those would also generally be fireproof and also very cheap. However, they require a decent amount of maintenance, just like wood. Maybe not necessarily to that degree, but more so than like steel or reinforced concrete. And they're certainly subject to things like weather and erosion and stuff like that. Perhaps not to the extent that wood is, but still. Also, it can be difficult to build with. But yeah, so rectangle, not so great. Arches, better than rectangles. Good for compression. Triangles, sort of all around. Better with tension than arches, but not quite as good at compression. And, strongest at the points. So like a very, very versatile shape. Triangles, the most versatile of shapes. Anyway, yeah. And then we went a little bit over the history. So, Rome and how Rome was sort of the big deal on the scene. And then they weren't anymore. And for a long time, nothing happened. And then iron happened. And that allowed for suspension bridges, which gave rise to the Brooklyn Bridge and the Golden Gate and a whole bunch of other bridges, stuff like that. Sometimes flexibility in suspension bridges can be a problem, like the Tacoma Narrows Bridge. However, it can be really helpful during an earthquake. So, like the Bay Bridge over here, which was a bad place to be during earthquakes in 1987, I believe, 1988. Yeah, not that fantastic. Anyway, now the actual bridge designer software itself. What about this? What's the why? Why would we do this? Why would we use this? How do you use this? What's it good for? Well, if you're so inclined, there is a design competition that we're holding. Just it's young engineers, nothing crazy. You have to use the 2015 Bridge Design Contest software. The least expensive bridge wins. Yeah, I know, but we're using the 2015 version, so just keep with that because they update like certain coefficients and stuff like that, and the simulation can change. Since it is just like an actual simulation, as opposed to actually building a bridge. Anyway, the least expensive bridge wins, and in the event of a tie, the earliest submission wins. Now, it mentions here that there is a $20 gift certificate to Adafruit. I'll have to speak with Mr. Dubik and see if that's still the case. That was the case last year. I just don't know if that's still going to be the case. You can also post your scores in Emoto, and you can submit as many designs as you'd like. Actually, you should post your scores in Emoto. You are more than welcome to submit as many designs as you'd like. Oh, really? Awesome. Congratulations. So you're pretty familiar with the software then? I imagine. But yeah, so yeah, definitely. You'll have to submit screenshots showing the number of iterations in your design and stuff like that. But, oh, you can't find it. Aw. The bridge design, you mean? Oh, the software. Um, guess maybe just, well, the the setup might be a good hint as to where it's kept, because if you run the setup, it'll ask you where you want to install it at a certain point, and it'll point to a default location. And if you know you hadn't changed it, you can, go to that point in the setup, cancel it, and then navigate to that folder in your computer. That's really weird. I did not actually change the um, slide. It just did that on its own. Anyway, also it's it's entirely possible that the stuff wasn't installed. You might just have to uh, reinstall it again. But regardless, there are avenues to get it up and running again. Speaking like Scooby-Doo. Ruh-roh. Anyway, let me go ahead and this is the middle school bridge. Let me go ahead and bring up a new design. No, I would not like to save. So when you first start up the software, you'll be brought to this dialog box. That gives you a few different options. You can create a new design, you can load a sample bridge design, and you can load an existing bridge design file. All pretty self-explanatory. Create a new bridge is to create a new bridge from scratch. Load a sample bridge is to load one of the sample bridges that exists in the software so you can get inspiration. And load an existing bridge design file allows you to load either one of the examples or one of your own creations. So you can, work on it over multiple days. That's the wonder of being able to save things on computers. One of the newest advances in computer technology, the ability to write a file to disk to store it for later and load it back up. Well, anyway, so once you create a new bridge design, click Create a new bridge design and click OK, you'll be taken to the design specs, design specifications, and this is what it looks like, minus the bridge in the background. That's normally not there, or that stuff on the right-hand side. That's normally also not there. The whole idea is you're a civil engineer working for the State Department of Transportation. Not really sure what state it is. But you are responsible for designing a truss bridge to carry a 2-lane highway across this river valley. Your objectives are to ensure that the bridge can carry its own weight, to include the weight of the reinforced concrete deck, plus the weight of a standard truck loading, and also to keep the cost of the project as low as possible. If you want to set a complete design specifications, you can click the help button, and it'll give you, oh yeah, see, you're a civil engineer. Okay, typo in the first paragraph. You have been assigned responsibility for the design of a truss bridge to carry a two-lane highway across the river valley shown below. There is a maximum height because there are overhead power lines. The water level is decently high. The bridge may cross the valley at any elevation from the high water level to 24 meters above the high water level. If the elevation of the bridge deck is below 24 meters, excavation of the riverbanks will be required to achieve the correct highway elevation. Oh, you found your old bridge? Nice. Provide clearance for the overhead power lines. The highest point on the bridge may not exceed an elevation of 32.5 meters above the high water level, 8.5 meters above the top of the riverbanks. And the bridge substructure may consist of either standard abutments or arch abutments. If necessary, the bridge may also use one intermediate pier located near the center of the valley. If necessary, the bridge may also use cable anchorages located 8 meters behind one or both abutments. Each main truss can have no more than 100 joints and no more than 200 members. So this is just all fairly basic stuff. Like you can't have more things than the stuff that we say that you can have for reasons. The bridge will have a flat reinforced concrete deck. There are two types available, which we'll see in a minute. Costs are calculated. Anyway, that's a whole lot of stuff. It actually kind of walks you through a lot of the stuff as you get this set up. So I'm going to go ahead and click Next. I've read the design requirements. Bam. Enter local contest information. Yours will probably have a blank deck cross-section and a blank elevation view. Mine is there because I set up a bridge already. Just so we're all clear, no, we are not entering in a local bridge design contest, despite the fact that we're having a young engineers competition. There's no contest code for that or anything like that. You know, you don't have to worry about that kind of stuff. So no, you are not participating in a local bridge design contest. Click Next. Here we can change stuff that will be affected in the elevation view. So the deck elevation, the support configuration, and everything related to that. Now keep note of the site cost. There's already a site cost of $62,700. So already, without even changing anything, our bridge already costs $62,000. I don't know about you, but that's pretty expensive. I mean, in the grand scheme of things, meh. Like this bridge I built for the middle school class is $405,000. I'm sure you could make one that's cheaper. But I'm just thinking $62,000. I wish I had that amount of money. Anyway, deck elevation. Changing this also changes the span because as we move the elevation down, they excavate out some of the valley and put the bridge there. So if we move it down more, look at that. Now the span is shorter. The span is shorter, and the span is shorter, and the span is shortest. Also keep in mind that this does increase the cost before we've even started building the bridge because they have to pay for the excavation. If you click the little triangle down here, you can expand it just to see how everything's changed. So excavation costs $102,000. That's a lot of money. So let me go ahead and bring it back up to maximum height. And as you can see, excavation costs are now 0, but the deck cost is increased. You are more than welcome to customize this to your heart's content. I'm going to keep it pretty standard right now as far as elevation is concerned for purposes of walking through this, but you know, you guys can do whatever you want. Standard abutments and arch abutments change how the bridge is supported. Standard abutments are just standard feet that the bridge stands on. Arch abutments have a setup for an arch underneath the bridge, which would provide more protection against compression. You can also change the height of the arch, which does increase the cost of the bridge, naturally. Adding a pier and increasing the height of the pier will increase the cost of the bridge. In fact, the pier can get pretty dang expensive. Not entirely sure why. I guess the abutments get thicker without a middle pier. Anyway, and then you can add cable anchorages for a suspension bridge. But again, those do cost money, and not too much money, $3,000 a piece. That's not terrible. Anyway, I'm gonna keep everything default and click next. Now we're given the deck material and the truck loading. The deck material is well, the material that the deck is made out of. By default, it's medium strength concrete, which is thicker and heavier. You can also have high strength concrete, which is thinner and lighter. However, it is more expensive by a pretty small margin, but a margin nonetheless. 51,700 for the deck to 56,100 for the deck. So a little bit under $5,000. You can see the cost update reflected here, 62,700 to 67,100. The way that it's loaded, that just has to do with how the bridge is tested. We'll just use the standard 225 kilonewton trucks. Click next. Then we're given a truss template. You don't need a truss template. However, it can be good to provide a sort of a starting point, a setup point. So we can have a Howe truss, Pratt truss, Warren truss, or the same versions but underneath the deck. Now, your truss template list will be different probably if you selected different setups for the bridge from me. If you selected a suspension bridge setup, by putting down cable anchorages, you're going to have different truss templates than I will. That's okay. That's just because those are the ones that are going to be applicable towards that specific, concept you have going for. So I'm going to select the through truss. I'm going to click next. The project name is Dennis H. Mahan Memorial Bridge. We can't really change that. Designed by and project ID. Designed by, obviously, you can put your name in there. I just put Young Engineers of Today. And project ID, Young Engineers of Today, whatever, doesn't really matter. But that's what I put down for that kind of stuff. You just give yourself a name for the project and give the project a name. And then click next. Finally, we're given this. This is just sort of a step-by-step process of how we're going to design the truss and finally the final product for the bridge. So design the truss. 1, click the Finish button to activate the drawing board. 2, click the joints. 3, draw the members. 4, run the load test to determine the strength of your design. 5, strengthen any members that fail during the load test. 6, optimize the design by minimizing its cost. That's the engineering process in a nutshell. So let me just go ahead and click Finish. And after 10 minutes of explanation, sorry about that, we're here. This is what we're looking at. Not really all that exciting, not really as graphically intense as maybe you were anticipating, and I'm sorry if that's disappointing. But this is how a lot of engineering software is going to look in many ways, except, without the cool simulation aspect of it. So, important things to note. We've got these gray circles here. We've got these lines here. We've got this thicker gray line with these gray circles in here, or I guess they're white circles. And then we've got this floating window of tools. Woo! The tools contains pretty much everything, the tools window contains everything we pretty much need to have in order to draw a bridge. In order to get into the more nitty-gritty of the stuff, that'll come later. There are some other things that we need, but we'll explore those as we get to them. There are a few things on the tools list, though, that I want to take a look at. There is this gray circle. If you mouse over it, it says select the joint tool. There is a gray bar with 2 gray circles. Mouse over it, select the member tool. There is another cursor. Mouse over it, select joints and members, and then there's an eraser. erase joints and members. So that is essentially what this truss is built out of. It's built out of joints and members. Joints being the things that connect the struts together, and members just being another name for the struts on the truss. Drawing a bridge is actually pretty easy. What I'm going to do is I'm just going to make sure I have the select the joint tool object selected. So I'll click on it, and I know that I'm drawing joints right now. I'm going to draw joints on each of these gray circles, white circles, whatever they are, along the top. Now, I'm going to draw the ones along the top, and I'm not going to touch the ones on the bottom. The reason being, this thicker gray line represents the deck. And the deck already has some joints built in. So we can't actually put joints here. See, if I try to click on it, nothing happens. I can put joints next to it, but I don't really want to do that right now because the joints cost $1,000 a piece. So right there, we've already got cost being added into our bridge. So now I've drawn all the joints that I really kind of need in order to get started on this bridge design. I'm going to go over to the member tool, and I'm going to start drawing the bars to connect everything. And it's literally just that. See, if I mouse over a joint with the pencil tool, I can click and drag to another joint, and that gets highlighted, and I get a little blue dotted line, and boom, I let go, I've drawn a member. And you just want to draw over each of these gray lines. And as you can see, if you're paying attention to the right-hand side of the screen as I'm doing this, there are more items appearing, or as you're doing this, whatever, there are more items appearing in the member list for obvious reasons, because we're drawing new members. The member list lists all of the members that are a part of the bridge. It also gives you some additional supplementary information that is useful at a glance. So let me go ahead and finish drawing this. Done. We've covered over all of the thin gray lines with thicker gray lines. And now let's talk about what exactly is going on over here in the member list. Now the member list contains information, like I said, at a glance about all of the different members that exist on this bridge. You've got numbers, and we can click on them and select that particular member. So like member 1 down here, that sort of thing. We've got material type, cross-section, size, length, slenderness, and compression force to strength ratio and tension force to strength ratio. Material type, it's the material it's made out of. In this case, carbon steel. That's what CS is short for, is carbon steel. Cross-section is a description of the cross-section of the bar. So if you were just to chop it in half, what would the cross-section look like? In this case, it's a solid bar. Size has to do with the length of the bar on a cross-section on one dimension. So essentially each member right now is 140 by 140 millimeters thick. Length is the length of the member in meters. So that is from one joint to another, not the thickness of it. Slenderness is the ratio of size to length. The higher the slenderness, the more slender the member is. So as you can see on this diagram, the diagonal ones are going to be a little bit longer than the orthogonal ones, the ones that go straight out or straight down or straight up or whatever. The ones that go out at an angle to a diagonal one are going to be slightly longer. We can see that reflected here. Most of these are 4 meters. If I click on one, as you can see, it's highlighting that particular one. If I highlight one of these 5.66 meter ones, it's a diagonal member, so it's a little bit longer. It also means that the slenderness is a little bit higher because despite the fact that it is a thicker cross-section, it is a longer bar by a greater margin. So it's a longer bar by a greater margin, so it's more slender, so the slenderness ratio is higher. Now these last two, compression force to strength ratio and tension force to strength ratio, are empty right now, and they will be empty until we run our first simulation. But they give us an idea of the forces that that each member is experiencing, and whether or not they're super bad and enough for a failure point. So now that we've done that, and now that I've done this whole drawing thing and I've shown the thing to you, I'm actually going to click on one of these first and go over here to the member details area. Member details will give you the details of any particular member, including the material, in this case carbon steel, the yield stress of that material, the modulus of elasticity for that material, so basically the strength and the how much force is required for it to permanently deform, and the mass density, how much it weighs. Then you get the dimensions. Here's a little picture of a cross section for it. So it's 170 by 170 millimeters. Most of these, I believe, are going to be 170 by 170 for some reason. That one's 140 by 140. I don't know why these are all 170 by 170. Because I certainly didn't want that to be. So let's change them all to 140 by 140. So they're all the same thickness now, because that's what it's going to be by default. It gives you the area, which is just 140 by 140 millimeters. The moment of inertia, which is how much it's to exert a significant amount of force on it. And then the cost. So the unit cost, $661.60 per meter. Since these are all generally several meters long, they're going to have a member cost of a couple $1,000s at least. So this one is only $2,000. This one is $3,700. And then you got a nice graph down here of how the strength to length ratio works. Anyway, let me go ahead and click on the simulation button. And we're going to see some interesting stuff happen. Namely, bridge gonna fail. Bridges are not supposed to do that. It doesn't matter if the bridge is still standing. That bridge will fail as soon as that truck drives over it. As it stands right now, we do not have a bridge that can support its own weight. It cannot support a dead load, which is kind of a problem. That's kind of an issue. With a small static load of a deck. I say small static load, with a static load of the deck. But regardless, it's not able to stand up under its own power. It's not able to stay standing under its own power. And that's not ideal. You'll also notice that the bars changed color as the bridge was, you simulate it by clicking the blue simulate button near the top. If you mouse over it, it's labeled run the load test animation. It's got like a blue sort of teal color. That's the one that allows you to run the simulation. Now, running the simulation, let me go ahead and bring it back to the simulation. They all start out white. Some of them turn red. Some of them turn blue. Yeah, sometimes it goes into the water. Exactly. Basically, the red means that it underwent extensive compression force. The blue means that it's undergone extensive tension force. So compression and tension. As you can see, it's kind of pretty looking, but the bridge experiences these forces differently in different parts of the bridge. All along the top, it's experiencing a lot of compression, and all along the bottom, it's experiencing a lot of tension. The vertical struts are experiencing tension. The diagonal struts are experiencing compression. Like, it's just all not fantastic. This is, whoop, oh, there goes my little pilot. This middle one is experiencing compression to a point of failure, which is why it bent. We never want it to bend. Bridges shouldn't bend. It's not what bridges are supposed to do. Certainly not the struts, not to that degree. At any rate, we can actually take a look at the member list and see now that everything has updated. Where did my little pilot go? Oh, there he is. Put you back on your Titan. Okay, so yes, looking at the member list, as you can see, the right-hand side of the spreadsheet has suddenly been updated with some very thrilling values. In addition, in order to make it maybe a little bit more thrilling, we've given those values colors. So here we go with the compression force to strength ratio and the tension force to strength ratio. Ideally, well, you actually want this number to be less than 1. That is important. If it is 1 or greater, that particular strut is experiencing failure. Kind of a big deal. Not what you want to have happen in your bridges. If it's less than 1, it's experiencing force, maybe even a pretty significant amount of force in the case of these two right here, which experienced 0.97, and this one which experienced 0.98. Whoa, really close to failure point. However, it still was fine. It stayed standing. But we're interested in the ones that are going over 1, because that means that they're experiencing too much force, and we must find a way to either reduce the amount of force that it's experiencing or strengthen it up a little bit. Now, generally speaking, we don't have a whole lot of control over how much force a given strut will experience. We do to a certain degree. We do by strengthening the struts around it so it doesn't have to carry as much weight. We can by distributing force among multiple struts. However, certainly when we're starting out and, in a real-life application, we have much less control over the force on a day-to-day basis that they experience. So the thing that we can control the best is the strength of individual parts. So that's what we're going to do. We're actually going to get started by making some of the weak points stronger. It kind of makes sense. You want to do that. You want your bridge to stay standing and not falling into the water. And we've got a couple different ways we can do that. So let's actually go back to the slideshow for a minute here, and we'll take a look at what they've got, because there's actually a very specific set of steps that we can go through in order to make this thing working just wonderfully. Oh yeah, that's also important to note. As you guys probably already figured out, the ones that are highlighted red or blue also get highlighted red or blue with the the red hashes or the blue hashes on the actual design picture itself. So there you go. So first things first, if I select one of these members on the sides, I get some information here. I see obviously that it failed due to compression forces, but I can also see that it failed pretty significantly due to compression forces. It experienced about 1.5 times the amount of force required for it to fail. In fact, this one was pretty dramatic. In the middle right here, it experienced almost 2 times the amount of force to make it fail, which is why it bent like that. But let's address these ones on the sides real quick. Now, in order to make this stronger, we got a few different things available to us. We can change the material it's made out of, or we can change the cross-section. We can also change the length, but let's just assume for the sake of argument right now that we're going to keep the length the same on everything. Although that's always something to explore in the future is maybe adding another node or something like that and making shorter lengths that are potentially stronger. At any rate, how do we go about doing that? Well, if we look at the top right here, we see we've got 3 drop-down menus. We got one that's labeled carbon steel, one that's labeled solid bar, and one that's labeled 140 by 140. What we're going to do is we're going to change it to 150 by 150. And as you can see, our entire load test result just went out the window because it's no longer valid. We just changed 2 things, and that changes everything. You think it might just change those particular members, but those particular members are also going to be able to absorb some of the load of the members around them, which means that the members around them are going to be able to absorb some of the load of the members around them, and so on and so forth. So the entire bridge will be affected by some degree or another by us just changing these two to thicker materials. So that's what we've done here. By going down to the 150 by 150, we have made the cross-section of an individual of these individual members thicker. It's a little bit hard to see, but it actually does get reflected in the design here as well. And if we click Simulate, it still fails, but it fails by less. Now we've got 1.12, and where is it? 1. No, where are you? 1.10, 1.12 and 1.10, 1.12, 1.10, whatever. So the failure rates have now actually gone, like the compression force strength ratio has actually lowered, which is good. We want that. We definitely want that. We want the compression force to strength ratio to be lower. So intuitively, we can kind of guess that yes, it will be lower, but you know, why? Realize that, and these members don't pass. I believe Bridge Designer 2013 is much more forgiving than Bridge Designer 2015. So the moment of inertia, which is that thing I was talking about over here in the member details, moment of inertia, that is a quantity, it's a value expressing a body's tendency to resist change. It's similar to, but not to be confused with, inertia, which is a property of matter by which it continues in its existing state of rest or uniform motion in a straight line unless that state is changed by an external force. Basically, the moment of inertia is, you can sort of think of it like how hard it is to change the direction of a ball versus inertia, which is the ball's ability to continue into, like, going the same direction, continue in the same direction. Oh, nice. Excellent. Sort of. It's sort of a combination of, that's sort of an okay descriptor of how those two are distinguished from one another. But yeah, congratulations, Cohen. The moment of inertia is expressed in this formula, which is super exciting, I know. But basically, base times height cubed divided by 12. Base times height being the cross-section. If we make the cross-section thicker, this becomes much larger. So does moment of inertia, so it becomes much stronger, as you can see. This is also a good point. In the moment of inertia formula, there are only units for base and height. Nothing in the formula talks about the type of material. You know, if you were just to type this into a calculator, you would get numbers that are way different than the moment of inertia that's listed here. The moment of inertia that's listed here also takes into account the strength of the material, which is another thing that can be, you know, utilized and accounted for and stuff like that. But anyway, let's go ahead and make these both a little bit thicker. In fact, let's go ahead and select all of these and make all of these 160 by 160. I can select multiple ones by holding down Control and clicking, or I can select multiple ones by dragging a box around them. Anyway, go to Simulation, and look at that. The truck is willing to try it, and it failed. But hey, we made improvements. Now, as you can see, the failures are pretty much restricted to the middle of the bridge, and the failure values are much, much, much lower. So if we change this to, you know, 180 by 180, as you can see, it does a little bit better of a job holding up. As the truck goes, bam, that side fails pretty spectacularly. Things are bad, but that's okay. At first you don't succeed. Build a better bridge. And not quite. Make those 180 by 180. And that part failed. Those two failed. So if we make those thicker, those should do a much better job of withstanding. And just barely, the truck makes it across. Magical. But yes, we'll spend a little bit of time going over the other concepts that are behind the scenes on this on Monday. And, we'll spend a little bit of time with Bridge Designer in general. But otherwise, that's going to do it for today. So let me go ahead and give you guys the poll questions, and then we'll leave it open for question and answer time and, that whole deal. So yeah, first poll question incoming.